Ok, bienvenue. Merci d'être venu. Welcome. Thank you for coming. So, we have a big program today. Last time we showed a very important theorem, which is basically that the energy of the ground state is a functional of the density. In other words, if you're given the single particle density, you know the ground state. And you see that's quite a remarkable achievement because, it says we don't need the full wave function. But to be able to solve this minimization problem, we need to know this function, what I call the f of m. That is the Legendre transform of this. So it needs to minimize all the wave functions that give the same density for the kinetic energy and the potential energy. So we know it is universal. So in other words, I can do it as it's just the density I need to vary. Here it's the kinetic energy, here is potential energy. So, but it's still very difficult to know what this object is. So to make this a practical scheme, Kohn and Sham have proposed to expand the density into a set of one-body orbitals, and there was some non-interacting system, and to minimize with respect to these orbitals instead of minimizing with respect to the density. So, for example, in this basis of orbitals, then the kinetic energy is just this. So this piece is approximated by this piece. So today I will continue a little bit to describe how it's done in practice and to show that this is written in such a way that there's a functional that we don't know that's called the exchange correlation functional. But since it's universal, it means that it should work for all materials. So, I mean, it's sort of a trial and error approach, but there are exact formulas that tell you, given a many-body system, what do you need to compute to get this exactly. And it turns out to be related just to the density correlation function, but for all coupling constants. So it's partly trial and error, and it's partly actually doing the work. So I will, once I show you what is this exchange correlation functional, I will tell you what people are doing to get better functional and show you how, what are the limitations of density functional theory and how many-body theory can help. And then we will move to Model Hamiltonian. Hubbard, the Hubbard model, the Kondo model, I'll discuss what the Model Hamiltonians are, what are the assumptions behind this, and that the new physics that we have not seen up to now is the physics of spin fluctuations. We have talked a lot about charge fluctuations, but not about spin fluctuations. And then we'll solve the model in the two limits, the limit of no interaction and the limit where there's no kinetic energy. Okay. So this model is a sort of toy model that that can be made more interesting, in fact, but it's a toy model that embodies the competition between potential and kinetic energy. Okay, so any questions for last time or? Okay, so let's move on then. Okay, so this then for this functional, what do we write? For f of m, we write that it is approximately, well, no, I mean, I will put this as an exact statement for now. It's equal to the Kohn Sham kinetic energy. And then it has a Coulomb interaction here. So there's a piece of the Coulomb interaction that's trivial. It's just the Hartree contribution. And in the case where we had a uniform background here, it gave no contribution. But for general cases that are inhomogeneous, it's actually very important. So we write it explicitly. So it's integral d cube r prime times n of r prime divided by 4 pi epsilon 0 r minus r prime. So so that's when I mean n of r here, I mean this quantity. Okay, it's written in terms of the Kohn Sham orbitals. And then we put all our ignorance into this function now, exchange correlation as a functional of n. Okay, up to now I've written a completely unknown function in terms of a completely unknown function, so there's not much progress. So what is this exchange correlation functional? We have an exact expression for that. I mean, it's just this minus this. Okay. Now you see there's the difference between the Kohn Sham and the exact kinetic energy comes in the difference. Now there's another thing that comes in, which is the Coulomb interaction. And the Coulomb interaction we can approximate by the Hartree piece, but there's also an exchange. Well, I mean, this is for self energy, but here there's an exchange also. So E exchange correlation of n can be again, it will be an exact statement, is equal to the exchange part of the Coulomb interaction written in the Kohn Sham basis. So that's minus, and there's a mistake in the last version of the notes. I will correct today. I'll send an updated version, d cube r prime, and then you have phi Kohn phi phi Kohn Sham of I. Oops, I forgot that you need to sum over ij. Here we have n over 2 orbitals. My board is leaving me. Sum over ij, sum over sigma of phi Kohn Sham I sigma of r, phi Kohn Sham j sigma of r, phi Kohn Sham of I sigma of r prime, phi j sigma Kohn Sham of r prime divided by 4 pi epsilon 0 times r minus r prime. So what happens here, you see, the phi I sigma is at position r and r prime at the same time instead of being at position r. So in other words, there are 4 field operators, and if you do the Wick contractions that you have worked on in the homework, you see that there's something that looks like this actually, because you have a G of 2 prime, G of 1 prime, and there's also an exchange, which is related to G of 1 2 prime, G of 2 1 prime. So this is the exchange piece, and this allows the Pauli principle to be satisfied actually. So when the spins are the same, you can do this this exchange. When the spins are different, then there's no exchange contributions. But voila. So that's the first term. And then, so that's the exchange. And then there's a correlation piece, which basically is contains what I was saying, the difference between this exact kinetic energy and the Kohn Sham kinetic energy, and also any error we might have done with this functional. So, but we know that there is this functional exists. So we will put all our ignorance into into the rest. And now what I'm writing is the local density approximation for this functional. What that means is that this thing that is left here will be integral dq bar. It's very hard to write here, sorry. Times some constant, times the density n of r. And it turns out, and this, I'm not sure I have a good reason for this, that it's a 4/3 powers. I mean, it can be justified in terms of Thomas Fermi screening, but I don't know how to do it on the spot here. So this basically, you have to find this constant by solving this problem. So the problem is now well defined in terms of minimization, because, okay, I can minimize with respect to these orbitals here, and then this LDA, and then, okay, then I have this here. I have the Kohn Sham orbitals that come in here. Here I have the Kohn Sham orbitals again, and here I have the density that is here. So everything is written in terms of Kohn Sham orbitals. So I can look at the minimum. So looking at the minimum is taking functional derivatives with respect to the phi's, and what you find are equations that look like Hartree Fock. Okay. So now, how can you improve this? So this is local density approximation. You see, so this functional depends only on the local density. Now, how would you get better exchange functionals? Well, you see, if I put the Laplacian of the density, it's still, a sizable, a correct functional of the density. And I can put gradients. I can put, a gradient is a vector, and this is a scalar, so I need to have a gradient square. So you can do you can increase the number of parameters here that are necessary. So for example, if you put more parameters, it's called the generalized gradient approximation. And then there's a functional that is very, very popular that's called a PBE, which stands for Perdue, Burke, and Hans and Ops, who is a professor at the University of Montreal, actually, in chemistry. And so there are several ways you can fix these parameters. One of them is that the chemists, they take molecules where they know they can measure the ground state energy by doing chemical reactions and so on, or at least differences in chemical. Excuse me. And then you can solve this Kohn Sham problem for the molecule, or even just the atomic level is the same problem. It's the same functional. And then you fix the problem, the constant empirically. So that's one way to proceed. The other way is to look at the electron gas in an inhomogeneous situation. You force the density to vary, and you compute this quantity exactly, for example, using Monte Carlo methods. And then you compare these quantities. So any method that you have that can be used to compute this quantity is a method that can be used to improve this local density approximation. So is that that okay? So you see, I'm treating this very superficially, but I want you to know that this is sort of the basis of modern electronic structure calculations. Now, we want to know not just the ground state energy, we want to know excited states. Okay, once you minimize these orbitals with respect to these orbitals, you get the differential equations. And these differential equations that I say are like Hartree-Fock equation. You have Lagrange multipliers that make sure that these phis are normalized, and you end up with something that looks like an eigen problem. So there would be eigenenergies for once you find these the eigenorbitals, there would be corresponding eigenenergies. Okay, so there's an energy associated with every one of the orbitals of the final solution of the Kohn Sham problem. So you can say, okay, what happens if I excite an electron? How much energy is needed? You would be tempted to say that it's the Kohn Sham energies, but it's not. It's not. Why? Because this is just an auxiliary problem. If you're lucky, if the interactions are not too strong, and this is a good approximation, then the excitation energy will be good. So let's see how good they are. I will show you some experimental and theoretical results. Let me share my screen. Okay, so what is this? This is the calculated gap. So the gap, then a single particle gap. How much energy does it take to take one electron? These are insulator or semiconductors. How much energy does it take to kick one electron from the ground state to the first excited state? So this is the gap for various, as I said, mostly actually semiconductors, but semiconductors are just insulators with small gaps. We see like, and the LDA, yes, I don't know why there are negative gaps here, but if you look at the local density approximation, you see that it can be pretty bad. For example, here for MGO, it predicts 4 electron volt, and the result, the experimental result, where is the experimental result? Yeah, okay, no, the experimental result is the dashed line here, and every semiconductor is shown. The location on the dashed line is shown here. Okay, so that's the prediction for LDA is 4 electron volt, and if I go to the dashed line here, well, it's I don't know why MGO is not on that line. Where is MGO? Is it on that line? No. The gap is much larger. So here it makes more sense to look at that point where we have aluminum nitride, and the gap is here, and the LDA prediction is there. Okay. So now, what best way to think about this is to think that this set of orbitals, phi k, is sort of a basis to do the calculation. Okay, and it's a good basis because we've tried to make our best. So now what we do is we start with this basis, and we do the Gwu approximation. In other words, we compute the self-energy. You know, the Kohn Sham energies will be modified by the self-energy. And the self-energy we compute in this Gwu approximation. Okay, in other words, we use the Kohn Sham orbitals to compute the density fluctuations, and then we compute the self-energy using using RPA, if you want. And then you get the blue dots. you see that it's a huge improvement compared with LDA. And here is another approximation, which is again GW, but what they call self-consistent quasi-particle GW. What does that mean? It means that you assume in this calculation in RPA, you remember we put unperturbed propagators. We put G0 if you want with the electron gas, but we can put G0 with the Kohn Sham energies. But in reality, that should be a self-consistent problem, but it's a killer problem. It's too difficult. So what they do is they assume that these are quasi-particles. In other words, they put the Z, that we talked about for quasi-particles. And then with the self-energy, they compute with the quasi-particles, and they make sure that it is a self-consistent problem. And you see they get even better agreement. So I think this is pretty much state of the art. At least in 2006, I've been to a meeting in 2019, and people still mention that as quite an achievement. So you see, there is if you want to do realistic calculations for real materials, you don't do just the electron gas. You have to go through this more complicated process of finding good eigen basis to start the calculation, and then you do many-body perturbation theory to get better agreement with experiment. And I forgot to unshare. Okay, is that clear? Are there any questions? Okay, so now we move to model Hamiltonians, and you will see later that this sort of branch, which sort of starts from a phenomenological approach, in fact, can also later be used in the density functional theory. In other words, at this level, we used sort of elementary methods of many-body theory that were invented many decades ago, like RPA and so on. And we improve the agreement with experiment. And then when we have even more correlated materials, we need more sophisticated methods than just a random phase approximation. And so it is useful to work with model Hamiltonians that are quite challenging, more challenging than the electron gas, and to try to find methods to solve it. Okay. So one of the first model Hamiltonian that was a challenge was the Kondo problem. So what is the Kondo problem? It is related to national pride, I would say, in the sense that the Russians were selling gold. They had lots of gold. And then there's a question of the purity of gold. And one simple way to measure that is resistance. I mean, there are more sophisticated ways these days, but if you don't have sophisticated instruments, you just measure resistance. And then what happened is that when they measured this resistance, they found that it was going to, the resistance as a function of temperature was going to something very small. So they were very happy with that. And then, whoops, it went up. Okay, so why does it do that? So it turns out this is what happens when you put magnetic impurities in a metal. So the model was very simple in some sense. People tried to understand this. The Russians kept that secret because they wanted to sell the gold, but was discovered eventually. So it's just you put a magnetic. So you assume you have a metallic. Okay, you have a metallic band here, and then you have some magnetic impurity. So what is a magnetic impurity? Well, it's just something that has a spin. So they wrote the Hamiltonian for a conduction band, just sum over k, epsilon k, c dagger k sigma, c k sigma. And then you write an interaction J times S, Z, S, not Z, S vector. Dot, so this S is this spin thing, and then you dot it into the spin of the electron. So the spin of the electrons at position 0, let's say, is just the sum over all k values of it's local. So C dagger k alpha sigma alpha beta ck beta, where these are Pauli matrices and alpha beta are spin indices. Okay, so and this so this spin is also a quantum spin. So what Kondo did is just perturbation theory on this. And then he said that in third order, so you have to be patient. If I remember correctly, I think it's third order. There was a logarithmic divergence. It's as if the scattering of the electrons on the impurity became logarithmically divergent. So this was a challenging problem for a long time, and the most satisfactory solution came with Wilson, who won the Nobel Prize for the renormalization group. So he applied renormalization group ideas to this Kondo problem. And the idea is that, I mean, there are simpler ways to do that were proposed by Anderson. It's called Anderson and Duval. It was called Foreman's scaling, which explains this in a relatively simple way. But if you look at what it amounts to in terms of perturbation theory, it means you have to sum perturbation theories to all orders. You see, when you have the log of temperature, for example, that comes in T0 over T, and so when T goes to 0, then there seems to be a divergence. But when you have when the real answer is T to the alpha, then you see that you can write this as T as an exponential, I'm sorry, of alpha log T. And then if you are doing a power series in temperature, then you get 1 plus alpha log T plus 1/2 alpha log T square, etc. So if you have a series that has a lot of logs here, log square, etc., then sometimes it is just a syndrome, I mean, of the fact that the real answer you're looking for is like this. Okay, so you can find the exponent here, and so there are ways to resum these logs systematically, but what the physics of the Kondo problem in the end is just that the conduction electrons form a singlet. So this is the spin here, and I have the spin of the conduction electron, and it forms a singlet with the with the impurity. So in the end, you don't see the spin anymore. In other words, what the resistance does is this: it goes down and then it saturates. And so this is resistance as a function of temperature. So when you have this saturation, is because you have formed this Kondo singlet. Now you can see it also, instead of having a J here, you can just say that there's a cost to U for double occupancy. So if U is large enough, you get to this, because then there can be only a single spin there. And then it's called the Anderson model. So it turns out that this toy model that explains some experimental fact will be very useful when we do dynamical mean field theory later. I mean, it will be much of dynamical mean field theory is based on methods that have been developed to solve this problem of quantum impurity. So an impurity in a background. Now the other Hamiltonian that came was the Hubbard Hamiltonian. So it was motivated by the fact that if you look at LDA prediction, or the simplest band theory you can think of for certain metals like nickel oxide, NiO2, it should be a metal. So you do all the sophisticated things you can, you do the simplest thing you can. It always gives a metal if you do band electronic structure or band structure calculation. And if you do the measurement, you see it's a very good insulator. So that's a very big problem. And it was known, it was found already in 1937. So in 1937, Piles and Mutt proposed that the reason it's an insulator is because of very strong Coulomb repulsion between electrons. In other words, if you think of a half-filled band, okay? A half-filled band has on average 1 electron per site, right? If you are in this situation and there's very strong repulsion for 2 electrons being on the same atomic level, at some point it will jam, it won't move. And that's called a Mutt insulator. So the idea of Mutt the idea of Mutt was just that if you have this large energy here, U, for repulsion, the electron can still travel a little bit. So if you had a single band, now I draw density of states as a function of frequency. So the LDA band, let's say, is something like this. Now, if I have a strong repulsion, it means that I can travel without avoiding double occupancy as much as I can. So I get this. But then I have an amplitude to travel on states that are doubly occupied. So it's as if this band splits in two, if you want. So n of omega as a function of omega. So the view of Mutt, for the Mutt transition, how do you go from a metal to an insulator, is just that these two things come here when you reduce U. This separation is U, and then that becomes a metal. or you can see it the other way. Now the view of Brinkman and Rice was that the way it comes about is that you have in the metal, let's look at a particular wave vector, right? So if we look at A of K, K fixed, A of K and omega, there's a quasi-particle peak here with a weight Z, right? And there's some background. So the view of Brinkman-Rice is that Z goes to 0. So their view was that they did some approximate calculation and that M star goes to infinity. Z goes to 0. Okay, now there were slate boson methods that I won't show by Cotillard and Ruckenstein that predicted something a little bit different. That is based on it's a generalization of an approach. It's another name that you will hear often. That Gutzwiller. But in the end, the picture that is accepted now is the picture of dynamical mean field theory that I will show you. And the dynamical mean field theory gives a picture that is intermediate between these two things, actually. Both phenomena come at the same time. I mean, both views are correct in some ways. But the transition, contrary to this and this, is not second order. It's not that the M star goes to infinity continuously and this goes continuously. It's a first order transition. And you can see both phenomena at once. Excuse me. So that's a bit an overview of where we are going, or what are the challenges, if you want, that go beyond dynamical mean field, beyond the electronic structure calculation. So the Hubbard model was in fact invented not only by Hubbard, but by André-Marie and Gutzwiller at the same time, basically. And I guess Hubbard was quick into suggesting all sorts of solutions and so on. So the name Hubbard model has stuck. And in some ways, this Anderson model that I was talking about is also the Hubbard model, but for just one impurity instead of the whole lattice. So let's assume that we do this program here that I suggested. We have the Kohn Sham orbitals, and we write that's the best orbitals we can, and we write the Hamiltonian with the Kohn Sham orbitals. Okay. So we know the Hamiltonian. But first, let's discuss the basis. Okay, so I'm talking here about the Hubbard model. I will talk about the assumptions a little bit later. So, so the basis is a block basis. Okay, if we have a material with, you can do this for chemistry, what I explained. But for us that are looking at bulk materials, what we want to do is to have a block function. So the Kohn Sham orbitals in the end will give block functions. So block functions are labeled by a band index and by wave vector. Okay. So it means that I can expand the field operator psi of r. I can expand on the band index and the crystal momentum. and I get R and K times the destruction operator in state, and then now I put the spin in spin sigma and state nk. Okay. But the interaction is better written in the basis that looks more like the atomic basis, look more like real space, right? Because the interaction U is on the atom from what the physics we just discussed. So instead of using this block basis, we're going to use the Vanier basis. Okay, so what is the Vanier basis? The Vanier basis is this. So we get W for band N, and at location R is located at site Ri is just equal to the Fourier transform basically of this. So it's 1 over square root of n sum over k of e to the I k dot r minus ri times this block function. Let me call this phi nk of r. So I have phi nk of r. Now there's some ambiguity, it turns out. I mean, you can, here I have kept the label n, but suppose I want orbitals that are local, that are quite localized around Ri. I have some freedom here. What I could do is a linear combination of these different n. So for a given for a given k here, I could have a matrix, a unitary transformation that goes from, you know, where this would not be the band index anymore. It would be some other index because I'm using some combination. So this is called maximally localized Vanier orbitals. And there are procedures to find them maximally localized, was invented by Vanderbilt. But we'll not worry about these details now. I just want you to know that there's some ambiguity in defining Vanier functions. Okay. So now suppose we want to compute the kinetic energy in the Vanier basis. So what we would do is we would write the field operator psi sigma of r as a sum over n and ri of w n r minus ri of c sigma of n ri. Okay, I dropped the vectors there. And now if I want to compute the kinetic energy, so I want to compute the kinetic energy operator. So I have integral d cube r psi dagger sigma of r minus grad square over 2m. And usually we put the lattice potential here. So L of r times psi sigma of r. Now I do this expansion. Okay, for psi and psi dagger, I write this. So what will be the final answer? So the final answer will be that this is equal to sum over n ri sum over m rj of c dagger n ri sigma, and I have a sum over spins And here I have the integral d cube r, because it's the same r everywhere, of the Vanier function of n of Ri, r minus Ri, times minus grad square over 2m plus v lattice of r times n, okay, star times wm rj of r minus rj times the c of sigma m rj. Okay. I've just used this expansion here in this expression. So the next step is this. I write now the kinetic energy operator as sum over sigma, sum over n m, sum over ri rj of c dagger n ri, and then I have some matrix T of n ri, m rj, c m of rj. Okay, so we still have to write the Coulomb interaction, so be patient. Here we will place ourselves in a situation where if I look at the electronic structure, so I look at the Kohn Sham energies. So I will write the energy here as a function of wave vector k. I have some spaghetti of bands, and assume that I'm in a situation where one of the bands is alone. Okay, so I have an energy window here where there are no other bands. And now I focus on this band. And I see, okay, this is where the interactions are most important. Because we saw that the Lindard function, for example, we were taking at we were looking at things that were happening near the Fermi energy, remember? So let's assume that we are in this situation. Then you see there's a big simplification. We can look at just one band here. So let's drop we can drop the band index completely and just focus on this one band. And then this I will write as there was a spin index here. I will write as the sum over I j of c dagger I t I j c j, where this is our emission matrix. Okay, this is just a shorthand for this. Okay. Now what happens with the potential energy? So the potential energy, I simply do again this, what I'm erasing right here. I'm just expanding the field operator the same way, okay? So what will happen then? It will happen that, okay, this is the kinetic energy operator. And now the potential energy operator, V, will be equal to sum over sigma prime, 1/2, and then I have I, J, V, K, L, C dagger, I sigma, C dagger, J sigma prime, C L of sigma prime, CK of sigma. Okay. So these go together. And you remember we have to switch things here to get rid of the minus sign. So so now you see, if you want, you can write this in this basis here. And so there will be an integral over R, an integral over R prime. So the integral over R will go with V of R minus R prime. The integral over R prime will go with V of R minus R prime. So this is just some overlap integral. Okay, so I have these orbitals that are at R, these orbitals that are at R prime. I do the integral over R, just like I did here, but over R and R prime. And okay, I get the same way I got some matrix here that was some integral to do. Here I have a matrix that's some integral to do. Okay. So here we have the So we have this one band model. Now you see if the solution, once you, in the Kohn Sham problem, once you solve the Kohn Sham integrals, you're just populating Kohn Sham orbitals to fill all electrons. In other words, you have some non-interacting problems. It's a single Slater determinant. Okay. Now, a single Slater determinant, even though these are Kohn Sham orbitals, are very good orbitals, and this can be made small by having good orbitals, the solution is not a single Slater determinant. You see why, right? Even if I diagonalize this, what this will do is to, kick two electrons out of some two states and put them in some other states. Okay. So a single Slater determinant cannot be a solution of this problem. It can be the solution of that problem, but not of this problem. And remember, a Slater determinant is just is equivalent to just filling orbital, filling the vacuum with the creation operators. Okay, now what the Hubbard model? So you can think of Hubbard that says, okay, it's too complicated. So let me write down a problem I can solve this weekend. Okay. And so it was done in 1964, and we're still trying to find the solution. Okay, it's solved exactly in infinite dimension and in one dimension, but not in arbitrary dimension. So what Hubbard said is, well, okay, the most important elements here will be those where everything is on the same site. Okay. So he said, I can do this weekend. So you have I here, I, okay? And then this becomes I. This becomes the same site, I. And now I call this U. And now what do I have? Sum over sigma prime. You see that when sigma prime is equal to sigma, this is two destruction operators at the same place, so it's 0. So so the only non-vanishing term will be when sigma and sigma prime are different. Okay, so I'm left with V is equal to 1/2 sum over sigma. Sum over sigma. Then I have C dagger sigma, C dagger sigma bar. So if this is up, this is down, and vice versa. C sigma bar, C sigma. So let me get, then I have sum over all sides. I forgot here. I had the sum over IJKL, and now I'm left with just the sum over I. So now the two terms are equal, right? If I have, so I can get rid of the 1/2 here and just write this. I can write this as up, down, down, up. And now up and down commute, so, or anti-commute. So I'm left with V equals sum over I. I don't have the sum over sigma anymore. And I have U and up and down. Okay. I. So that's the sum of these two terms is the Hubbard model. Okay, what's new in the Hubbard model is spin fluctuations. Because I can, you see, I can write n up times n down. I can write as 1/4 times n up plus n down minus 1/4 n up minus n down. It's n up and n down commute, so these just work like numbers, square. So you see n up square cancels with that, n down square cancels with that, and then there's a cross term that's equal to 2 n up and down with 1/4, it's 1/2, and then there's minus and minus, so that gives an up and down. Okay, so that's charge fluctuation, so that's rho square if you want, and that's spin fluctuation, that's SZ square. So that's a big difference with the electron gas. So the Pauli principle is very, and we use the Pauli principle here, it's very important when you talk, when you look at short range, because two electrons at the same spin cannot be at the same place. And that has a huge consequence that the spin fluctuations will become the name of the game here. In fact, they will be much more important than charge fluctuations. Okay? So I'm supposed to give you a homework. So the homework will be, I will write it for you. I will send it to you. The homework will be basically to do these two limiting cases. So Hubbard said he would do it on the weekend. So you can do these two cases in a few very easily, in probably 2 hours. So the solution is in the notes. So U equals 0, the solution is in the notes. So that would be part of your just, repeating what I did. And the T equals 0 is also in the notes, but it's done with the equation of motion. And I will ask you then to do it like in the notes, but also using the layman representation. I think it's quite useful to do it using the layman representation as well. So you will solve these two cases. And I would have liked to say something about this very quickly. If you look at the solution will be that the Green's function, suppose you're at that filling, will be equal to 1/2 times 1 over, once you analytically continue, omega plus I eta minus U over 2, and plus 1/2 1 over omega plus I eta minus plus U over 2. So you see that if I look at the spectral weight, I have two delta functions, one at minus U over 2 and one at U over 2. So you see the electron is at, I have a single, it becomes momentum independent because it's there's no hopping. And in fact, so whatever momentum I look at, I have the same thing. So I have two levels. And the electron, if I look at this in real time, if I look at this as a propagator, then you see there's a sum of amplitudes. The electron can propagate in this and this at the same time. If I project an energy eigenstates, then I have either minus u over 2 or plus u over 2. Extremely, extremely different than what I would get for a single particle, right? A single particle, I will have a single peak if I give k, and this peak will move. Now, whatever the value of k, I get the same result because it's completely local. So it doesn't move with k, and also it's split in two. So that's the idea of these Hubbard bands I was talking about, is related to this, is an, you know, sort of an extension of this thing. Okay. And also, if you want to write this as a self-energy, you will see that the self-energy sigma, so suppose you take the usual form with the self-energy, you'll see the self-energy is equal to u squared over omega plus I eta. So in other words, there's a pole at omega equals 0 in the self-energy. So instead of having a self-energy that is you know, a power series in omega, we get a pole. So we're getting rid of the pole, the quasi-particle pole with the self-energy, and splitting this pole in two. Okay, so there's a lot of physics here that I think that it's so important. I don't have time now. I will redo it when we start. 2 weeks from now, I will discuss this a little bit more. You will have done the solution here, and we will discuss this this interesting piece here before we continue. Okay, so I see you not next week. I see you the week after, because there's the American Physical Society meeting. And remember that we're changing the time. So I hope to see you at the right time. So I will stop the recording. And as usual, if you have questions, please stick around.